Now let's talk about the next level, or the lowest level in the memory hierarchy, which is virtual memory, which is kept on the hard disk or hard drive. So virtual memory gives the illusion of a bigger memory, and main memory acts as a cache for the hard drive. So here's a picture of the memory hierarchy again, and now we're talking about the hard drive, which is we also refer to as virtual memory. It is slow, but very large and inexpensive. So here's a picture of a hard disk drive, which probably none of you use now, but hard disk drives used to have these magnetic disks with a read-write head that would take milliseconds to move around, right? Kind of in mechanical time frames. And then there's solid state drive shown here, which is mostly what people use today in their systems. So programs use virtual addresses. There's an entire virtual address space stored on a hard drive. A subset of that address space, of that data, is held in DRAM, or main memory. The CPU translates virtual addresses into physical addresses, in other words, DRAM addresses. Data not in the DRAM is fetched then from the hard drive. In addition to allowing us to effectively expand the amount of memory we can access, virtual memory also offers memory protection. So each program has its own virtual to physical mapping, and two programs can use the same virtual address for different data, for different physical addresses. So programs don't need to be aware of others running. The virtual memory system takes care of that. One program or virus can't corrupt memory being used by another program. So there are some analogies between caches and virtual memory. So cache has a block size, right? The number of words that we access in a single cache line or cache block. In virtual memory, we call this a page. It's the amount of memory that's pulled from virtual memory from the hard drive into physical memory, or DRAM, at a given time. And so the block offset in a cache, we have what's called a page offset. So that tells us which word within that page we're actually accessing. In caches, we call it a miss. In virtual memory, we call it a page fault. And in cache, we have a tag. In virtual memory, we call that the virtual page number. So again, physical memory, or main memory, acts as a cache for virtual memory. So page size is the amount of memory transferred from the hard disk or hard drive to the DRAM, to main memory at once, to DRAM. Address translation determines the physical address from the virtual address. A processor generates virtual addresses. And we'll talk specifically about what those are. And a page table is a lookup table used to do that translation from virtual to physical addresses. So here's a picture of what this might look like. We have virtual addresses on the left, and some of them, the ones in blue, these pages in blue, are just on the hard drive or the hard disk. But some of those pages are in physical memory, also called main memory. Or physical memory called main memory, and we can access them from the processor, and particularly to pull into the cache. So most access is hit in main memory and physical memory, but programs have the capacity, or the large capacity, of virtual memory systems. So it seems like a lot of memory and fast, but really it's because of using this hierarchy between virtual memory that's stored on the hard drive, and physical memory that's stored in DRAM, in the main memory.